Hey, hi everyone. So I'm going to do the introduction. In the meantime, hopefully everybody comes in. It's my great pleasure to have Professor Moses Charikar from the Stanford University today. Moses got his PhD also from the Stanford University. Then he was a professor at Princeton for several years before coming back to Stanford. So he is doing amazing work on many different topics, including searching and indexing massive high-dimensional data, efficient algorithms for computation in high-dimensional statistics, and optimization for machine learning, approximation algorithms for discrete optimization, convex optimization techniques for non-convex combinatorial optimization problems, and many other very interesting works. His work, he has won many awards, including the Best Paper Award at Fox, Colt, and Soda, the 10-year Best Paper Award at VLDB, and the 20-year Test of Time Award at Stock. He was a recipient of the Paris Kanellakis Theory and Practice Award. He was named the Simons Investigator in Theoretical Computer Science and an ACM Fellow. Thank you so much, Moses, for accepting our invitation today. Very much looking forward to your talk.
Thank you. Thanks, Baran, for the very generous introduction. It's a pleasure to be here. I was just reflecting with many friends I have here that it's been more than a decade since I came to UCLA, so it's great to be here and great to see many familiar faces. I want to talk about something I've been working on with a bunch of great collaborators here, Alexander Lasota, Prasanna Ramakrishnan, Adrian Vera, and Kangning Wang. Kangning was a postdoc at Stanford when we started this work, and he's now at Rutgers. Pras is a student at Stanford. He's a force of nature and someone you should definitely look at when he's on the job market next year. So I had a somewhat provocative title and zero knowledge abstract maybe that didn't really say very much about what I'm going to talk about. The idea was to get many people in the room, and I see that a bunch of people took the bait, so we'll see if the talk lives up to the hype. All right, so the topic of my talk is elections. So we're going to be talking about systems by which people express their choices and choose a winner. So you're going to have candidates, you're going to have voters, and these voters are going to express their preferences by ranking the candidates. There are multiple ways in which you might organize elections, but the kinds of elections that I'm going to talk about are those where every voter says, here's my ranking. So you can think of the input as a bunch of rankings that different voters give, like so. And these are ordered. There's a first choice, there's a last choice, and there's a complete ordering of all of the candidates. So that's what the voters do. And there's a basic question in social choice theory is how do you use this information and come up with the winner of the election? Or maybe another way to phrase it is how do you find the most broadly appealing candidate? Okay, so it's a very basic question, and as you can imagine, people have pondered this question for a really long time. I'll say a little bit more about that, but I want to make the point that elections are everywhere, and normally the first thing that you think of when you hear the word election is you think about political elections. Of course, that's a very important application area. We use elections to choose representatives. We use elections to elect people into our government. But there are many other situations where elections appear as well. We use elections when we decide, who we hire. We use elections when we choose the winners of awards, or in some sense, there are lots of low-stakes elections that happen every time you go out to a restaurant and decide what to eat, who would like what, or as my student Pras likes to do, he actually uses some of these mechanisms to decide what to play when he gets together with his friends. So there are a number of different situations where elections arise. These are just decision procedures that take the preferences of participants and come up with some outcome, right? And I'd like you to think about elections in that way. So, another reason why you might care about elections is just in the past year, there's been an explosion of interest in using such mechanisms in AI, and that's because there's a very important procedure that's used in fine-tuning AI models, which is you look at the outputs of these models and you give them to human raters. They tell you which ones they like, which ones they don't like, and use these human preferences to figure out how to fine-tune the model. And there's been a bunch of papers, these are just a sampling of some of the papers that appeared just in the past year, saying that, well, this is exactly what social choice theory has been doing for a very long time, and we ought to be able to use some of the ideas that appeared in social choice theory to the setting of fine-tuning LLMs. So there are many reasons why you might be interested in elections. I gave you a bunch of them, so hopefully now you're all motivated to listen to the rest of the talk. Okay, so let's go back to the question. How do we choose the most broadly appealing candidate, right? And one approach, very natural approach, is to say, perhaps we should, sort of a very basic principle that we might use is majority rule. You could say, well, we're trying to find the most broadly appealing candidate. If the majority prefers A over B, then we shouldn't choose B rather than A, right? There's no reason to prefer B because majority is saying that they prefer A over B. This is a very basic thing, a principle that you might start with. But unfortunately, there's a problem with this. And there's a problem that was pointed out by Condorcet in 1785. So way before the birth of computer science as a discipline. And in fact, there are even some writings that suggest that this paradox appeared in the work of Ramon Llull in the 13th century. So people have been thinking about elections and mechanisms for elections for centuries. And Condorcet pointed out this fact, which might now be obvious to maybe a bunch of you, you've seen this before. The majority rule is fundamentally is not consistent. Okay, so it's possible that if you work with this principle that we said about majority rule, no matter which candidate you pick, it's possible the majority prefers somebody else. So if you've never seen this before, it's pretty easy to construct an example where this happens. And you can just do this with 3 candidates, 3 voters. If you just have cyclic preferences, like I've shown, it's possible that there's no one clear winner. So if you had to pick, let's say, candidate 1, then you'd say, well, 2 people prefer candidate 3 over candidate 1. So 2/3 of the people prefer candidate 3. You say, well, okay, let's go with candidate 3 in that. But if you do that, then 2/3 of the people prefer candidate 2. And if you go with candidate 2, then 2/3 of people prefer candidate 1. So you have a cycle, right? That's a problem. And in fact, this is called Condorcet's paradox. And you might say this looks like a theoretical construction. It gets worse, by the way, and we'll get to that. But you might say this is sort of just a theoretical construction. Does this actually happen in practice? In practice, do people actually see this kind of thing? So first of all, it's hard to get your hands on actual election data where people have this express their preferences in this way. But there are studies of real elections. Here's one, pretty recent. This one's from 2018, which actually studied, for example, this one was the 2016 Republican primary, and they did find actual examples of these Condorcet cycles in an actual election. So it's not just a theoretical construct; it is something that actually appears. I should say, I'm really an outsider to social choice theory. I'm not really an expert by any means, but my understanding is that people in this area, some of them take the view that these things can happen, so we need to come up with mechanisms that that handle these things. And some of them take the view that maybe we should come up with a model for how people vote that just rules out Condorcet cycles. And both of these viewpoints are prevalent in this community. I'm going to, my training is that of a theoretical computer scientist, and I sort of have a very pessimistic, worst case view of many things. So I'm going to try to make no assumptions. I'm going to make no assumptions about the voters. I'm going to say voters can behave as they want. They can give us anything as their preferences. Our goal is to come up with a mechanism that works well, and we'll see what that means. Okay, so that's my perspective. All right, so back to this issue of Condorcet cycles. So I showed you an example where you can have 3 voters, 3 preferences, and 3 candidates, and no matter which candidate you pick as a winner, 2/3 of the people prefer somebody else. Well, once you realize that, you can actually construct an example where it's a lot worse. You could have 100 voters and 100 candidates and have a cycle on those. And then no matter which candidate you pick, 99% of the voters are going to be banging on your door and be unhappy and say, why didn't you pick this candidate? All of us prefer this candidate over the one that you picked, right? I mean, I didn't have space on that slide to draw 100 voters and 100 candidates, but here's an example with 10 voters and 10 candidates. And in this one, no matter who you pick, 90% of the voters prefer somebody else, right? So if you pick 5, then, well, 90% of them like 4. Okay, so that's kind of bad. If you're the person that has to decide who the winner is, you're in this difficult spot. You can't appease everybody. In fact, no matter what you do, almost everybody's going to be unhappy, right? Okay, so what can you do, right? You need to relax, take a breath. But we're also going to relax the problem a little bit. Okay, you're going to say, how about this? Instead of picking one winner, how about we announce a few winners of the election? And I'll explain in a second why this might make sense. So let's think about what that would do in this one example. Okay, so in this one example that I had, if instead of announcing 5 as a winner, if I announce 5 and 10 as a winner, then I say, okay, how many people would prefer a different candidate to both of the people on my committee of winners? Well, then now 40% of the voters prefer 4 over either 5 or 10. 40% of the voters actually also prefer 9 over 5 or 10. But the fraction of unhappy voters that can coalesce around one alternative that they prefer over everybody on your winning committee, that's gone down from 90% down to 40%. Okay, so suddenly you don't have a majority of voters banging on your door and telling you, why didn't you pick this one candidate that we all like? Okay, that's great. So, so before we do that, let's just let me just sort of pause for a second and say, this idea of picking multiple winners is something that actually does appear in practice in many situations, right? You might have winners of grants, fellowships, the committees that award multiple winners, multiple fellowships, hiring, you hire multiple people, ordering food at a restaurant, you don't order one dish, you order multiple dishes, and you have in political elections, you have multi-winner districts. When you elect people to a school board, you have multiple representatives and so on and so forth. In fact, there was an article in the New York Times just from January this year arguing that a lot of the polarization that we have in the country today, the issues that arise from this two-party system, are because we have every district has one representative. And so if you have a small majority in one direction, that party gets that district. If instead you had multiple winners, you could have a system where you had proportional representation, and that might be the cure to some of the ills that we see with the political system today. So anyway, I'm not a political scientist by any means. I don't want to pontificate on that, but there are lots of reasons why you might want to have multiple winners to your election. So back to our more prosaic examples. This might be a pruning step, right? It might be that your election mechanism doesn't really decide on the winner, but just comes up with a short list. And then all the stakeholders can look at that short list and then deliberate and then decide who the winner is. And in doing that deliberation, they might even change their preferences, or they might, decide they agree with somebody else's viewpoint. So this might be an intermediate pruning step, which is perfectly fine. It could be nominees for a prize, it could be interviewees, could be, this could be the primaries or runoffs. Okay, so if we're sold on this idea that let's try to pick multiple winners, then here's the problem. Condorcet's paradox basically says if you pick a single winner, it's possible the majority prefers somebody else. Okay. Instead, let's relax the problem and let's pick a few winners. Now, to me, this feels like a very natural question, and in some ways, it's a question that Condorcet could have asked when he came up with this paradox. But somewhat surprisingly, this is a question that only arose in recent work, like a 15-year-old paper that suggested that this was an interesting question. And they asked, can we choose K winners so that less than 50% of the voters are unhappy? Okay. By unhappy, I mean they all prefer some other alternative to everybody on the winning list. All right? Okay. So another natural question is, what's the smallest K that you can pick? So you have an arbitrary election with arbitrary preferences. What's the smallest K that you can pick so that you have this guarantee that you won't have a rebellion with more than 50% of your voters coming and banging on your desk or your door and telling you you messed up? Like, how come you didn't pick this one candidate that we all like? All right. So what's the smallest K that you need to pick? And more generally, 50% is just a threshold. You can pick some other threshold, alpha, and say what kind of, how large does K need to be in order to ensure that the number of unhappy voters is at most alpha fraction. Okay. All right. So for each K, presumably there's an alpha. What's the trade-off between K and alpha? But for most of the talk, we'll just talk about alpha being half. All right. So like I said, this is, I think of this as a very natural question. It could have been asked by Condorcet, but as you'll see, we actually tackled with fairly modern tools that weren't available to Condorcet at the time if this question had been raised then. So we're going to use game theory and the probabilistic method, and I'll say a little bit about that a little bit later. Okay. I should also say this, our work builds on some recent work on something called approximately stable committee selection. If you don't know what that is, it doesn't matter. I'll say a little bit about some of the methods, but mostly I want to focus on the results. Okay, so are there any questions? By the way, feel free to interrupt. I didn't say that before, but if people have questions, happy to hear them, or happy to go on. I don't see any questions. Okay, so let me show you what's known, what's the landscape for this problem. So Condorcet's paradox says you can't pick one. Okay, if you pick one, almost everyone will be unhappy. And this paper that raised this question also showed that you can't pick two. So if you pick two, it's possible to come up with an election where no matter which two you pick, 2/3 of the voters will be unhappy. Okay, so 2 doesn't work. What they also showed is that, and actually, by the way, there are multiple constructions of this fact. They give one construction, but there are other constructions as well. Okay, so what they also showed is that if M is the number of candidates, then log M always suffices. So, and it's sort of the obvious algorithm that you might think of if you were thinking about this problem. And it's just a greedy algorithm. So you say, okay, let's look at the candidates. Let's look at, how do they do in pairwise contests. And if there was one candidate that won all the pairwise contests with everybody else, you just pick that one and you're done. But there may be none. How about just picking the candidate that wins the most number of pairwise contests? that seems to be a good person to have on your committee. So let's pick this person. Okay. And now this person defeats more than half or half of the remaining candidates. But there's some other set that this person doesn't defeat. You just recurse on that subset. Right? So now you focus only on those guys, and you repeat. Pick a candidate that defeats most of this subset, and so on and so forth. So you have a bunch of iterations. Each iteration you pick one candidate. Each iteration the number of candidates goes down by a factor of 2. So in log m iterations you're done. And so that's basically the state of the art when we started working on the problem, which was a few months ago, by the way. We haven't been at it for that long. So what's the right answer? You can't pick 2. You can pick log m. So the correct answer is somewhere between 3 and log m. Right? This is the kind of problem that you can actually relate at a party, and I've done that a few times. This is the point when I stop and ask people, what do you think is the right answer? So maybe this is too big a group to ask, but are there any brave volunteers that want to volunteer their thoughts? No? All right. Okay. So what we showed was that you can pick 6. Okay? You can pick 6 candidates such that less than 50% of the voters will be unhappy. I have to say, we were a little surprised. I mean, I was a little surprised. I thought going into this problem, log m is surely the right answer. And, you know, we just had to figure out how to prove a lower bound of log m. Right? But we managed to show that you can actually pick 6. So we didn't improve the lower bound. So the right answer is 3, 4, 5, or 6. And more generally, if you have a particular threshold alpha that you're interested in, then we can tell you, our methods give you some bound on how many candidates you need to pick. The bound looks a little complicated, but it's basically something like log k. So if you pick k candidates, the number of unhappy voters, the fraction of unhappy voters behaves like log k over k for small values of k, and behaves like 10 over k, let's say, for large values of k. So there's some dependence. And the lower bound that I mentioned, where if you pick only 2 candidates, 2/3 of the voters will be unhappy, that lower bound construction can actually be generalized. In general, that construction tells you that if you pick k candidates, the fraction of unhappy voters will be at least 2 over k plus 1. So there's a gap between the upper bound and the lower bound. The lower bound is the red curve here. The upper bound that we have is the blue dots. And so one thing that's interesting is that already we can show that we can pick 2 candidates so that we avert this Condorcet's nightmare that I described. So earlier I said, look, no matter who you pick as a candidate, it's possible that almost everybody is unhappy. Not true if you allow yourself to pick 2 candidates. So if there is a way to pick 2 candidates so that not everybody is unhappy. The fraction of unhappy voters is bounded away from 1. I should say that, you know, we started out thinking about this question. I thought there's got to be an easy way to show this. I still don't know an easy way to show this. Okay, so we have a somewhat convoluted proof that gives us our result, but even the result for k equals 2, I would love to see a simpler way to just establish this fact, and I don't know of one. Okay, sorry, question. Okay, so you know, on this, if you look at this graph, it crosses half at about, you know, between 5 and 6, and so that's why our result is 6. Right? The number of Oscar Best Picture nominees, you might know, is 10, and that's where it is. It used to be 5, by the way. I don't know if you remember, but before 2010, there were 5 Best Picture nominees that the Oscar committee announced, and then they increased it to 10. And I don't know if any of you actually remember why. So they increased it to 10 because in the previous year they got a lot of blowback. There were 2 movies, Dark Knight and Wall-E. And everybody said, how come you didn't put these movies on the list? What are you doing? They said, you know what? Let's just increase the Best Picture nominees from 5 to 10. And so that's where we are. Of course, even now, people are unhappy, and they always find reasons to complain. So this was about this year's nominees, but you know, that's life. Some people are going to be unhappy. That's okay. All right. So let me just give you a brief overview of the proof, and then if I have time, we'll spend some more time on the proof towards the end. But our proof goes through a few different steps. Okay. So I'll just explain these steps very briefly now, and then if I have time, we'll go into them in a little bit of detail. So the first thing is the following, right? Our proof says that there is a way to pick k candidates so that the number of unhappy voters that all prefer some alternative A is small. We don't know how to prove this directly. But if you ask yourself a question about a distribution, change the question a little bit and say, can I find a distribution on subsets of k candidates such that for this distribution, the fraction of unhappy voters that coalesce around any one alternative A is small? That, it turns out, is easy to do. Okay. In fact, this is an application of the min-max theorem. It's the version that we use is not the simplest version of the min-max theorem, but a slightly souped-up version of the min-max theorem. We're just saying the distribution is over subsets of at most k. Yeah. So if you allow yourself a distribution over committees of size k, and then you say for any one alternative A, you ask the question, what fraction of the voters prefer A to a committee that's sampled from my distribution? We can ensure that quantity is bounded by 1 over k plus 1. And actually, this is very simple, and we do that. So we wanted one committee of size k. Instead, we get a distribution over committees of size k. Okay, and this turns out to be easy. Now we use this distribution as a measuring stick, in some sense. So we use it as a measuring stick both to measure how good a committee is, and to also bound how attractive an alternative candidate is. Okay, and so there are 2 facts that we prove about this about committees and candidates. So what we show is that candidates tend to be low with respect to the distribution. On the other hand, committees tend to be high with respect to this distribution. Okay, and then this may not make much sense right now, but if I have time, I'll actually elaborate on this. But this is what we show. So, you know, we have this distribution. We now use it to quantify how good a committee is and how bad candidates are. And then finally, you know, what we say is that on average, committees are high, but now we prove the existence of one committee that's good enough for us, and this is the committee for which we prove the result. Okay, so this is like think of this as an existence proof, and that's how it works. All right, so these are the components in the proof. All right, so you know at this point I kind of gave you. How am I doing on time, by the way? Okay, good. So, you know, at this point, you know, I explained the result to you. I don't know if you're really interested in the proof. If you are, I might give you some more details. But here's a message you might want to take back, especially the faculty in the, you know, in the audience. So, you know, so I want to give you one useful interpretation of this that you might want to carry back. So, you know, I'm sure there are many situations when you know, you're called to your chair's office and your chair tells you, I'm going to put you on so-and-so committee, okay? And in the past, you might have complained about this, you might say, please don't put me on a committee, I'm too busy, or don't put me on a committee, it's a waste of my time. But now you have a new excuse. So I'll tell you the new excuse. The new excuse is you got to say, don't put me on that committee. It's got more than 6 people, and it's provably ineffective and inefficient. Okay? You can identify the people who should be on that committee, and then you can say, look, it's not just me. A majority of the people wouldn't even want me on this committee. So hopefully you can go back with that, one real useful takeaway from the talk. If that wasn't fun enough, I want to give you a little fun digression, which we actually discovered after we wrote the paper. So if you look at the paper, it's not in there, but a little special bonus for you. I want to change topics, move away from elections and talk about a completely recreational topic, a fun dice game. Okay, so somebody presents you with these 4 dice, and these are not the usual dice that have 1, 2, 3, 4, 5, 6, but they have these weird special configuration of numbers on their sides. So there's this dice, and this dice, and they say, well, why don't you pick a die? And then after you pick a die, I'll pick a die. And then we'll roll the dice, and the person who gets the higher number wins. Okay, that's the game. So let's think about this a little bit, because this is not the usual dice setup. This is a little weird, funny dice. The blue dice seems to be very easy to reason about. It's a pretty boring dice. It always produces the number 3. So that doesn't seem like a good dice to pick. And in particular, if you pick the dice, the blue dice, the red dice seems to be better, because 3/4 of the time, for 4 of the 6 outcomes, it gives you a number 4, which is better. So 2/3 of the time, the red die is going to beat the blue die. Right? Great. So maybe you should pick the red die. Well, if you think about it, the green die is actually better than the red die, because there's some chance that the green die will produce a 5, which will beat the 4. But then there's also a chance that the green die will produce the 1s, which will beat the 0s. Okay. So if you do the calculation, the green die beats the red die 2/3 of the time, and now you kind of get it. You can anticipate what's going to happen. The purple die beats the green die 2/3 of the time, and the blue die beats the purple die 2/3 of the time. This is a cycle. So in fact, people might seem very gentlemanly in allowing you to pick the die first, but in fact, you're at a disadvantage if you're the one who has to pick the die first. Right? And this phenomenon is called non-transitive dice. If you're curious about this, this is something that mathematicians have obsessed about for a few decades now. It was popularized by a paper of Martin Gardner in 1970, Scientific American, where he wrote about this. That construction that I described actually is due to Bradley Efron, who's one of the seminal figures in statistics. He came up with this construction of 4 dice. And we know a lot about intransitive dice. All kinds of questions that you might care about, people have figured out in a lot of detail. There was a polymath project that Tim Gowers ran during the pandemic around intransitive dice and so on and so forth. So it's kind of a fun recreational topic, very unintuitive little corner of probability that people have thought about. Okay, so this game actually was also there's a funny story about this. So apparently Warren Buffett is a big fan of these intransitive dice. So he used to at least carry around some of these in his pocket, and would use it to trick his friends into paying for his lunch, as if he needed the extra money. But so he would, for example, sit down with Bill Gates and go play with him. You get the first pick, and then apparently, so the story goes, Bill looked at this and said, there's something funny about these dice. You should go first. Okay, so, all right. Okay, so this is not fun, right? This is a weird, this is kind of a little party trick, and it's rigged against the first chooser, right? What if we change the game a little bit? What if we switch the game to give an advantage to the first person? Instead of picking one dice, how about we give the first chooser the flexibility of picking multiple dice, right? And will allow the value that we'll assign to the first chooser is going to be the best of all of their rolls. Okay? So you get to pick multiple dice, and the second player picks just one. Hopefully that tilts the odds in the favor of the first player, right? You would think. So the question is, can an adversary still trick you into this game, give you a really bad set of dice, such that even if you have this advantage, can you somehow say that, no, I'm going to pick some number of dice, announce a number, so that no matter what the adversary does, you will have the upper hand as the first chooser? Yes? Oh, should it be? Okay, good. Okay, great. I should go and check that. As is usually the case, when you're up here in front of the audience, your IQ drops by 50%. So I'm not going to fix that in real time, but I'll take your word for it. By the way, I should say that there's some, if you're actually interested in the recreational aspects of this, there are all kinds of fun constructions. So there is one construction of these intransitive dice where if you roll twice, the domination cycle reverses. So you can trick your friends in all kinds of weird ways, and you can go read up about it. But anyway, so I'm suggesting a different modification of this intransitive dice game. Okay, so in fact, this dice game is, at least the version that I described, where the first one picks multiple, is really voting in disguise. There's a close connection between the voting problem that we discussed before and this dice game that I've described. And I'll let you think about the correspondence, okay? But basically the dice correspond to candidates, points in the sample space correspond to voters, and the order in the sample corresponds to preferences. But with that hint, I think you should be able to figure out what the connection is. Okay. So in fact, these non-transitive dice are an example of Condorcet's paradox. And our result in this dice setting says the following. Okay, even if the adversary gave you an arbitrary set of dice, okay, and even if the adversary had the power to correlate the outcomes of the dice in an arbitrary way. So these are not independent dice anymore, but they're these weird dice that have correlations. Even so, you can always pick 6 dice. So as the first chooser, you'll have an advantage. Okay? And this version of the problem, the correlated dice problem, is exactly equivalent to the election problem. They're the same. I would say we didn't realize this. I think it was a math overflow comment somewhere that alerted us to the fact. And actually, Pras, my student, was talking to Adam Bouland, a colleague of mine, and Adam said, "This sounds like intransitive dice. Is there a connection?" So anyway, so just to say that it's a non-obvious connection, which we didn't realize originally, but it's there. Okay, now how am I doing on time? All right. I have a little bit I wanted to say about the proof, but I'm just wondering how much I can tax the audience. So how much time since I started, actually? 4:20? Okay, all right. Okay, so let me say a little bit about the proof for those of you who want to see it. Let's say there are 3 steps. Okay, and so the first step involves somehow constructing a probability distribution. So let me say a little bit about that. Okay, so what we really want is the lower bound says that no matter how you pick a committee of size k, at least 2 over k plus 1 fraction of the voters need to be unhappy. There are constructions where this happens. On the optimistic side, you might hope to construct a committee of size k so that at most 2 over k plus 1 fraction of the voters are unhappy. So this is the kind of statement that we would like to construct. And don't worry about the math notation. What I'm really saying is that there exists a good choice of a committee of size k such that the fraction of unhappy voters is 2 over k plus 1. I don't know how to prove this, okay? But I'm going to allow myself the flexibility of picking not one committee, but a distribution over committees of size k. And so this is something called, in the literature, it's called a stable lottery. It's a distribution on committees of size k such that for any other alternative candidate, the fraction of voters that prefer this other alternative candidate to a committee that's sampled from my distribution is bounded by 1 over k plus 1, as it turns out. So because I allow myself randomization, I can actually get a better bound. I can get 1 over k plus 1. Okay, now how do you prove this? In order to prove this, what we're going to do is we're going to use von Neumann's minimax theorem, right? So von Neumann's minimax theorem allows you to take this game and look at a dual game where this distribution naturally arises. Right? So what's the game? I choose a committee. You choose, the original game was I choose a committee, you choose an alternative candidate, and then we draw from this distribution and the voters compare. Okay? But it's equivalent to the dual version where you choose a distribution over alternative candidates. I choose a committee S, okay, and now we compare the two. Right? So what von Neumann's minimax theorem is saying is that these two are actually equivalent. Right? So now let's try to figure this out. You're going to pick a distribution over alternatives. I'm going to pick a single committee. What committee should I pick so that my committee does well with respect to your distribution? Well, the natural choice is to just sample from your distribution over candidates A. So if you have a distribution over candidates A, I'm going to sample my committee from that same distribution. And for this, it's pretty easy to show that the probability that a voter prefers, so you get one draw from the distribution, I'm getting k draws from the distribution. The probability that a voter is going to prefer your alternative to the best of my choices is 1 over k plus 1. Okay, it's not very hard to show that. It's an interesting exercise to prove it if you haven't tried to prove something like this before. Because that's how you get the 1 over k plus 1. Okay, first thing done. Second thing. Now, we're going to use this distribution as a way to quantify how good sets are, how good committees are, and how bad, let's say, individuals are. So this is how we think about it. We have this sort of visual of our distribution and the voters' preferences. So think about your voters' preferences as somehow represented by this column. Okay, so there's one column for each voter. And let's focus on one particular voter's column. So each committee is a block in this column. Right? The height of this block is exactly the probability mass that our distribution gives to that particular committee. Okay, and now the voter V has a preference order. For each committee, look at the favorite choice that the voter V has, and look at the ordering of the favorites in voter V's ranking. That's how the blocks are ordered. Okay, and then the candidates are slotted in between the blocks. So now, the key point is that voter V prefers an alternative A over everybody in S if the candidate A sits above S in this visual representation. Okay? And the point is, now we're going to argue that typically candidates are low down and committees are high up. That's basically what we're going to argue. So we're going to use this visual analogy and make this argument. Okay. So why are candidates low? Well, the point is that our first guarantee that we had basically says that the area under any one candidate is 1 over k plus 1, because that's the expected fraction of the voters that prefer A over a random draw from the distribution over committees. So that tells you that candidates in general are low. The area under them is small. Okay, so all we have to show is we have to show that some committee is high. Right? So let's look at the Green Committee. The Green Committee has some distribution. It has some positioning in all of the voters' rankings. Let's like reorganize this distribution to reorder the things. Okay, so what we want to show is that some committee is high. Now, look, we know that candidates are low down. The committee has some distribution. What's the best way by which a candidate can try to beat the committee? The best way for a candidate to beat a committee is to beat the committee on exactly the lowest portions of the committee's distribution. If we can show that even for the bottom half of the committee's distribution, the area under the curve is more than 1 over k plus 1, then we'll be done. That's basically what we show. Okay, so because the area under any candidate is bounded by 1 over k plus 1. So how do we find this high committee? Well, let's just look at a random committee. If you look at a random committee, it has kind of a random position in everybody's rankings. Okay, and you could think of it from the voter's point of view as the following, right? From a single voter's point of view, if you sample a random number between 0 and 1 and threw a dart at that point, look at where this dart landed. Now that's what the distribution over committees looks like from this voter's point of view. Okay, so and if sort of committee were independent, then a committee distribution would sort of look like this. It would look like a straight line if you ordered from lowest to the. And if it were really like this, then well, what's the area under the curve for the bottom half? It's 1/8. Okay, it's 1/8. And basically, this is what we show. We show that there is a committee that has area at least 1/8 over the bottom half. Takes a little bit of argument, it's not very hard. And this shows that k is equal to 7, by the way. Right? So this establishes the result not for 6, but for 7. And getting from 7 down to 6 involves some additional ideas, and you can look at the paper if you really want to see it. Okay. All right, so some concluding thoughts. There's a bunch of interesting questions. There's a gap between our upper bounds and lower bounds. Ross conjectures that the lower bound is correct. I'm not so sure, but it certainly would be very nice if that was the right answer. So, can you choose at most k winners so that the number of unhappy voters is at most 2 over k plus 1? I think that might be the right answer. Okay. So far, we haven't ruled out 3. It might be that 3 candidates might suffice to satisfy a majority. That would be very cool to show that. I don't know how to show it. As I said, one interesting question is, could you even give a simple proof that it's possible to pick 2 candidates so that the number of fraction of unhappy voters is bounded away from 1? Seems like a simple enough thing. I don't know how to prove it. Okay, and if you want to go down this route, let me just point out one simple, one obvious thing that you might think of is maybe this is a purely graph theoretic question, right? So if you ask the question, can you choose 2 winners such that at most 2/3 of the voters prefer any alternative? One way to attack this problem is to set up a graph theory problem. You have voters, you have the vertices of this graph are candidates, and you place an edge AB if there's greater than 2/3 fraction of the voters that prefer A over B. Okay. Now, one property of a graph where every edge corresponds to greater than 2/3 voters preferring one over the other is that it doesn't have any 3 cycle. This graph does not have a 3 cycle. In general, if you have a threshold which is not 2/3 but 1 minus 1 over L, then this graph does not have an L cycle. So this graph has high girth in the directed sense. It would suffice to show that for this case, any triangle-free oriented graph always has a pair of vertices which does not have any common in neighbor. Okay, and this is a very attractive property. In fact, we tried to prove this for a while. Turns out that this is not true. Okay, you can even look at the souped-up version where you say, can you prove this for a graph which has girth L? Turns out that this is not true. Either this is false, okay, and there's a paper. In fact, the paper says that for any k, for any L, there are graphs with girth greater than L. So for every set of k vertices, there is a common neighbor. Okay. And this is actually a very cool construction using additive combinatorics. So I haven't actually read the details, so don't ask me about how it works. But it just means that this proof technique is not going to work. Okay, so I just want to rule out one thing that you might try if you want to think about this problem. Okay, so I want to just end with some philosophy. So we have a lot of election baggage, I think, when we think about elections, which sort of limits our perspective. So when we think of elections as these very high stakes things, which are, and when we think about that, our thinking is fraught with all the political implications of elections and so on. But I think we should sort of move away from that and just think about elections as being decision procedures beyond politics. And I think they're just interesting mathematical objects that we should think about. And I hope I gave you one interesting perspective that we might have on elections. And just as other things that we study, in mathematics and discrete math, as theoretical computer scientists, graphs and post sets and so on, it'd be nice to understand elections too with that same lens. And let me end with a very British joke, courtesy of my British collaborator, Adrian Vera. So maybe this doesn't make sense so much to a US audience, but this is from an election in Britain. So they have this tradition where the winner of these elections, you have to go and stand in front of the news crew and so on, and all of the candidates line up when the results are announced. So there are all these weird characters who show up because they know that they're going to be in the news when there's a high-profile candidate. So there is the then Prime Minister Boris Johnson with Elmo and Lord Buckethead. Maybe that's the optimal committee. Actually, in this particular election, I think Johnson won 25,000 plus votes, and Elmo won 8 votes, and 59 votes, 125. So anyway, I don't think our methods would have actually picked this particular committee of size 3, but it's interesting to contemplate the possibility. All right, I'll stop here. Yeah. Yes. Yeah, great question. So there's a trivial answer to the question, which is, if you're interested in committees of size 6, you can try all possible committees of size 6, and you'll find a good one, right? Because verifying that a committee is good is very easy, right? You just have to see what fraction of the voters prefer any alternative. Try all the alternatives for this committee, right? But that's not a satisfactory answer. Like, I think of that as kind of the trivial answer. Maybe there's a better answer, and I don't know if there's a better answer. So it's a great question. Is there a good constructive argument that allows you to construct the committee in time that's better than n to the size of the committee? Yeah, it's a great question. So you want to say, is there an instance-specific bound? Like maybe for a particular instance of an election, there's a better bound, and can you do that? And honestly, we haven't thought about it. It's a great question. I mean, given that the answer is somewhere between 3, 4, 5, and 6 in general, it might even be the case that for this particular election, the answer might be 1 or 2. But yeah, there's a small sort of possibilities. And can we find the optimum answer for a particular election? It's a great question. We just haven't thought about it. Yeah. Yeah, that's a good question. We didn't think we couldn't come up with any nice clean characterization. We originally started with this formulation, and we said, okay, this seems like maybe it might be true, and we did work on this for a while before Adrian, who's our collaborator, pointed out, by the way, I have this paper that rules this out. It's not going to work. So we didn't think so much about this alternate formulation. Um, about whether we could sort of refine the question and say that it's not all graphs that you need to think about, but these very special kind of graphs. It could be that there's a way to refine the question so it actually has a good answer. Thought also. Yeah. Other than checking all the entire support of the distribution. Um, yeah, so I think if you just sample a few times from the distribution, we'll be fine. We didn't try to prove it, but I'm pretty sure it'll be okay. Because basically, a result can be thought of as saying a random draw from this distribution is good. Okay, so I phrase it as we prove the existence of a community, but in fact, a random draw from this distribution is going to be. So yes, you could do that and lose a little bit, but you won't lose that much. That's fine. But then, of course, there's a question of constructing the distribution as well, right? Which will be inefficient because you're the support, yeah, the support of the distribution is committees of size k. So presumably, you want a more efficient way to do that as well. Oh, could it be the right? No, k equals 3 could be the right answer. It'd be very cool if it was the right answer. Yeah. So when this paper in 2011 came out, there were a bunch of people that tried to understand what the smallest committee size was. In fact, the paper, they used this term Condorcet dimension. So they said the Condorcet dimension of an election instance is the smallest committee size. And there's at least one master's thesis where it was entirely focused on understanding what this was. And there was another paper that basically used SAT solvers to come up with interesting constructions. Nobody managed to improve on, yeah. So there were some alternate constructions were found. One based on kind of some number theory construction. There was another one that came out from the SAT solvers. It was much smaller than the original construction, but it didn't improve the known bounds. But who knows? I mean, maybe now we have much more computational power available to us. So maybe we could do something better. It would be very cool to do that. Okay, I'm going to declare victory. All right. Thank you.